Okay, let's spend a little bit of time just talking about some batteries and fuel cells and kind of understanding what all the parts are and where they're coming from. As a reminder, batteries are a galvanic or voltaic cell. They are spontaneous. Delta G is less than 0, E naught greater than 0. So we can have acidic or alkaline if we're looking at dry batteries. These are batteries that you guys have probably in devices you already have at home. I have no doubt that some of you have taken these apart and looked at them. I don't recommend it. It is full of chemicals, but if you ever had a battery break down, it breaks down because it starts corroding all that stuff on the outside of the battery. That's just the chemical reaction happening. It's just burst through the container that it was in. So let's look at acidic first. In acidic batteries, the zinc is an inner case as an anode, and we've got zinc being oxidized to zinc 2 plus and 2 electrons. The cathode is a carbon rod that's immersed in a moist paste of manganese oxide, ammonium chloride, and carbon. The manganese oxide is being reduced under the following reaction. In alkaline batteries, the zinc is still your anode as that inner case, so we've still got zinc being oxidized to zinc 2 plus. We've still got a copper rod immersed into that paste. That should say paste, by the way. I didn't realize that, I apologize. Moist paste of manganese oxide. But in this case, instead of ammonium chloride and carbon, we have potassium hydroxide, sodium hydroxide. One of those two, or a combination thereof, and carbon. Or a brass rod. The advantage to alkaline batteries is they tend to be longer lasting. The electron itself corrodes more slowly in alkaline conditions, so that's what you're going to see more often of is an alkaline battery. You've probably heard that term, just not thought about it much, but it's pretty common to use. The voltage on an alkaline battery is 1.54 volts. They have a longer shelf life than acidic dry cells, and they're rechargeable because they have little corrosion of zinc. What I mean by corrosion, again, is when you've got that battery and all of a sudden you open up and it's like all crusty all across it, and it's usually like colored like white. A lot of white happening in here. White is zinc oxide or the zinc corrosion product. It's just breaking it down. We can have your lead storage batteries. This is like a car battery. The cathode here is lead coated with PbO2. The PbO2 is being reduced under the following reaction as shown here. We've got 6 cells connected in series, 2 volts each, to give us an overall 12-volt battery. The electrolyte in this battery is sulfuric acid. It is 30% sulfuric acid, so if you've ever switched out a car battery, you know you have to be very, very careful to not get this on you, because again, sulfuric acid will burn through you and your clothes. When I was much younger, someone in my life was switching out a car battery for me, and he flipped around quickly by accident, and thank God knew what he was doing, because he quickly, very, very quickly stripped his shirt off of himself and threw it on the ground, and we picked his shirt up a few minutes later to look at it, and it was just in shreds because he had spilled the battery. Thank God the shirt protected me and he get out himself, because it could be really bad. If you've ever had your battery tested, you go into an automotive shop or you go for an oil change and they're like, hey, your battery's doing this well, you got this much life left on it. How are they doing that? They're actually measuring the density of the sulfuric acid that's in your battery. So the density of sulfuric acid is used to measure the charge left in the battery. 1.28 grams per centimeter cubed is considered normal. If they're telling you your battery's not performing well, your battery's getting low, it's because your density's off on your sulfuric acid. It's the way they're measuring it. You've got a solid lead sulfate adhering to your electrode surfaces. See here, lead 2 sulfate, and we can recharge these batteries by forcing the current in the opposite non-spontaneous direction, electrolysis process, right? Electrolysis of water can result. We can make hydrogen gas and oxygen gas. We've also got lithium ion batteries, really, really common now. They're rechargeable, they have a long life, they're very light, and they have excellent energy density. What we see here is the lithium ions here are actually migrating from the anode to the cathode. Again, electrons always travel anode to cathode, so we can see the electrons being transferred from the anode to the cathode, causing corresponding migration of the electrons from the anode to the cathode. If the positive charge is traveling, the electrons are going to follow. We've got cobalt 4 plus being reduced to cobalt 3 plus at your cathode. So your anode, you've got your lithium ions, your cathode, you've got your cobalt ions. If the battery is acting faulty, discharging, meaning like running out completely, pretty quickly, overcharging it, it's basically that the structure itself has been compromised. You've got your anode, your cathode, and your electrolyte, which is the material in between the two. And if one of them has been compromised or is not performing properly anymore, that's when you're going to have problems. That's when your battery is not going to behave. You can have, best case scenario, the battery just overcharges. Worst case scenario, your battery blows up. So why do they catch fire? Because you've short-circuited somehow, you've overcharged. The electrolyte itself is breaking down. The battery's just not good. Remember, batteries are a chemical reaction. They are contained chemical reaction, but they are a chemical reaction. And materials are not meant to last forever. So sometimes the materials just can't keep up with what we're doing anymore, and they're just done. And they have to be replaced. We've also got a breathalyzer here. We can see the breathalyzer instrument is also an electrochemical cell. We've got the suspect blows their breath through the system. It's looking for ethanol. That's the alcohol that's in regular alcohol that people are consuming, and it blows it across. We've got your anode, your cathode here. It's monitoring the consumption. So you blow the ethanol through, it oxidizes it, forming forming acetic acid. I apologize, CH3COH, acetic acid. So it's oxidizing it, forming acetic acid, and it's actually monitoring how much is coming through comparative to what should be in there for normal. It's like a comparison to a standard. So it's estimating your blood alcohol content through your breath. Pretty simple. Also remember that we say oxidizing because it's forming more or putting more oxygen into the sample. That is an organic way of saying oxidation versus reduction. If we increase the oxygen content in the sample, we have oxidized it. You can actually look at the electrochemical reaction here. It is in fact being oxidized by all rules, even those rules that we have talked about in this class about gaining and losing electrons, but this is basic gist of what's happening. It's oxidizing your ethanol into acetic acid and monitoring the content of acetic acid in the sample, separating out the two pieces across the anode and cathode, and then it gets an overall readout.